Мы хотим поздравить от лица приезжих из Дальнего Востока товарищей, коллег Владимира Михайловича с днем рождения, с юбилейным днем рождения. Ну, может быть, не все знают, что малая родина Владимира Михайловича – это Амурская область. Вот. Поэтому мы земляки с ним и особенно хотим поздравить его с днем рождения.
Спасибо.
Пожелать ему здоровья, успехов и на благо Родины. Я думаю, будем совместно развивать самый интересный экспериментальный проект.
Спасибо. Спасибо. I some translation that is day I call the Google Day because Google present me with a birthday, but real my birthday was 1 month ago. You understand? But in passport, really, Google Day, Bank Day, Yandex Day, and so.
Facebook. Okay, let us start our scientific session. First speaker is Nora Strotjohann, the multi-wave polar operator, IceCube, neutrino multiplet. 35 minutes for talk and 5 minutes for questions and discussion. Please.
Yeah. So yeah, I'd first like to thank the organizers for inviting me, to give me the opportunity to come here and give this talk. So I will tell you about the search for short transient neutrino sources with IceCube's optical and X-ray follow-up program. And I speak on behalf of the IceCube collaboration, which is around 300 people around the world. And I work at Zeuthen, close to Berlin, where we have a group of around 10 people who all work on follow-up in different wavelength regimes. So this is the outline of the talk. First, there will be a short introduction. Then I will explain to you about the detector and show a few results we've had. And then we'll come to what I actually work on, the optical and X-ray follow-up program. I will present one specific alert where also the master telescopes had an important input, and then it's the outlook in the end. The motivation to search for neutrino sources is that we want to know where those cosmic rays come from. So those are charged particles that hit the atmosphere at all times, and they come from all directions because they are deflected in space, so they don't travel straight. And we know that the one with the highest energies are extragalactic, but we don't know where they come from, so the sources are unknown. This shows you how neutrinos can help with finding the sources. So here we have some kind of source. We don't know what it is, but it accelerates protons. And then close to the source, protons can collide with each other or collide with photons, and then they make pions. And the pions decay, and we get gamma rays, you see here, and also neutrinos, which you see here. And so if we would find a neutrino source, we would be certain that this is also a cosmic ray source. For gamma rays, it's not that easy, because on one hand, they could be absorbed inside the source, or there are also different ways to produce gamma rays. So for a gamma ray source, you can't be sure it's also a cosmic ray source. So and this is the detector we are using to detect neutrinos. It's called IceCube Neutrino Observatory, and it's located at South Pole in Antarctica. And the glacier there, the ice shield, is nearly 3 kilometers thick. And we melted holes into the ice and lowered detection modules. So there are those so-called strings, and at the lower kilometer there are these large photomultipliers, And they form here a 1 cubic kilometer volume. And if you would put the main building of Moscow State University next to it, you have to put 4 of them on top of each other to reach the height of the detector. And so what happens is when a neutrino interacts within or close to the detector, it creates a secondary particle, and then this secondary it emits Cherenkov radiation, so blue light, and the light is then detected inside the detector, and you see here that it the light pattern allows us to reconstruct from which direction the particle came. So here's one simulated event. You see here that red colors means early times and bluer colors is late times. And then the size of this shows you how much energy was deposited there or how much light was detected. So here you can see that this is a muon traveling upwards through the detector. And we have 2 different kind of events. We call them cascades, and they look more spherical. And then there are track-like events, like the one you just saw. So they are elongated. And these are caused by charged current interactions of electron and tau neutrinos, and also by neutral current interactions. And for these, we can often measure the energy precisely because the event is not so large. It can be contained inside the detector. And when a muon neutrino does a charged current interaction, we get this track-like pattern, and there we can reconstruct the direction nicely, but often not the energy, because you see here that part of the track was maybe outside the detector, so we only see part of the energy. But for point source searches, these are better because we can tell the direction.
And what is the error box on the left, on the cascade-like event?
For the best cascades, it can be down to 10 degrees, but for others, it's 30 degrees or
All sky.
yes, basically all sky. And so these are 2 extremely high energy events, but the typical events we detect look more like this. So these have maybe 1 TeV of energy, but we can reconstruct them in the same way. So this is how we detect particles. Unfortunately, we also have backgrounds. So here you see cosmic air showers that hit the atmosphere. And in these showers, muons can be produced, but also neutrinos. And you can see here that atmospheric neutrinos can travel into the detector, and muons can also enter it if the shower is above the detector. So we need to get rid of this background before we.
I'm sorry, can we 2 words in Russian for the low people? Ну, таким образом, она говорит об IceCube на Южном полюсе, и она отмечает, что есть певные и темные нейтрино. У темных нейтрино у них хорошо определяется error box, 1 градус всего, то есть полностью в поле зрения мастера. Но певные нейтрино порождают каскад, который практически до 30 градусов, ну, то есть полнеба там. Да, то есть на самом деле вот мы имеем дело с нейтрино, которое прилетает снизу, сверху, пролетает всю Землю, и потом в этом льду порождает мюон, а мюон уже дает вот эту всю заряженную частицу, дает черенковское излучение. Ну, нет, темные нейтрино, там как бы отдельные нейтрино.
Что они измеряют больше, нейтрино или энергичные космические лучи?
Вот flux is more big, the neutrino
yes.
or background cosmic
Yes,
ray.
on the next slide.
Next slide.
So yeah, this is the background for track-like events. And here you see that yeah, from above there are lots of muons entering the detector. So those are these here created in air showers. So it's 6 orders more muons than neutrinos, 6 orders of magnitude. And then down here these are neutrinos, and so they come from all directions more or less. And yeah, 99% of them are atmospheric neutrinos, so also from air showers, and 1% are actually cosmic neutrinos. So we want to find those 1%, and so yeah, we have to find a way to get rid of the background. And the only difference between those two is that at the highest energies you only have cosmic neutrinos left. So the atmospheric ones have a bit lower energies. And so we managed to detect an astrophysical neutrino flux in 2013. And the method was really simple. So they used a veto. So every event that started inside this veto layer was rejected because it could be a muon coming from above. And events that started inside the detector, they were accepted. And then after this veto, they used only the highest energy events, so the ones that make a lot of light inside the detector. And you see here the spectrum we can make from this. So this is the energy and the flux. And yeah, the red band is the fit to the astrophysical flux after subtracting the background. And yeah, you see it's not very precise yet, because at the highest energies there are only few events. And this is a map of all high energy events which we have detected so far. So each of them has a probability of more than 50% to be astrophysical. And yeah, you see here that they come from all directions. This is the galactic plane, and so some might be galactic, but many are likely extragalactic. And we detect only about 20 of them per year. So you have to wait a long time to get a larger number of events. And all the blue ones are cascade events. So for these, there's a large uncertainty on the direction. So yeah, this is unfortunately not enough to find a point source, but you can look at the spectrum. So this is the astrophysical flux, and this is the background. And if we've only measured the flux up here, but if you extrapolate it, you would expect that there are several hundred of events at lower energies where there's a lot of background. But yeah, we can use these to look for point sources. So this is the latest result from point source searches. This is the significance map using 7 years of data. It's only track events, but also lower energies. And yeah, also here, so here we believe that there should be several thousand of astrophysical neutrinos, but yeah, we still don't see a source.
But what are those pitches, concentrations?
I think in the
Looks like some source already, not yet.
No, it's not significant. If you consider that you look in every direction, then that you get this trial factor. So yeah, it could be by chance. And one way to be more sensitive would be to if you would know some sources where you think they make neutrinos, you can look in that directions. And here I show 2 examples. So this is blazars and this is GRBs. So yeah, one colleague of mine looked at blazars from the Fermi catalog, which yeah, as you can see here, and he compared whether there are more neutrinos coming from those directions. But he didn't find anything, and so at most 6% of the flux we detected can be from blazars. And yeah, for GRBs it's similar. In the time where we took data, around 1,200 GRBs were detected. And here we look for neutrino emission while the GRB emits gamma rays, so during the T100. And also there, no correlation was found. And you see here that the sensitivity we have would be a factor of 100 below the flux we detected. So yeah, only 1% of the flux we see can come from these bright GRBs that are detected by in gamma rays. So yeah, now we come to my part of the work. So we set up a follow-up program to do it the opposite way. So we detect neutrinos and then we trigger telescopes to see whether there's any source there. And we can only look for short sources. So here are examples. We could either look for GRBs, where the neutrino emission is expected to be around 100 seconds, so similar to the gamma ray emission. And those would be detectable in gamma rays, but they could be faint, but also they would have an optical afterglow. Then there are predictions that some core collapse supernovae have a jet inside. So yeah, we could try to look for that. Because here neutrinos would manage to get out of the stars, but gamma rays maybe not if the jet is not powerful enough to get out.
Because very far, maybe, yes?
No, but it could be that the jet is broad, so it's not so collimated. Or
more collimated?
No, less.
Less? Oh.
And then it's not strong enough to get out of the star. And here we would expect to see an optical supernova and the neutrinos at the explosion time. And then, as you know, there are active galactic nuclei, and they can also, some of them have short flares, and they would be detectable at all wavelengths. So now we try to search for such short sources. And we use all track events from the northern sky. And here, this is the spectrum of all events within 1 year. So it's 100,000 per year. And if we would compare this to the flux that we think is there, we would expect 600 outgoing muon tracks per year. So much more background than signal. And what we do now is we wait for a transient source to happen somewhere in the northern sky. And if we detect 2 or more neutrinos from this source within 100 seconds and 3.5 degrees, then we get an alert in real time. The delay is about 30 seconds. And then if it's significant, we can trigger telescopes, either optical to search for an afterglow or a supernova, or the Swift satellite to search for an X-ray afterglow. And here you see the number of doublets we've detected so far. So this is two events from the same direction in 100 seconds. But this can also happen by chance. It could be 2 atmospheric events coming from the same direction. So the boxes show you how often we expect it to happen by chance. And the dots show you how often we actually saw it. And so, yeah, from background only, we would have expected 314 neutrinos, and we did see a few more, but yeah, this is not a big difference. So it could be that all the doublets are from background. So we cannot prove there are such short sources. But yeah, we had one very interesting alert 1.5 years ago, where we had a large follow-up campaign. So I will now show you this alert. It was detected in February 2016, and it was for the first time not only 2 events from the same direction, but 3. And you see them here on the sky map, and this is the combined direction. And yeah, it was the first time that this happened. But yeah, so all events have rather low energies, so in the TeV, below TeV range. And also, unfortunately, one event, number 1, is a very large angular uncertainty. So, and then I calculated how likely this could happen by chance. That just 3 atmospheric events come from the same direction. And here it shows you how often we would expect this since the start of the follow-up program. So at that time, the follow-up program was already running for more than 2,500 days. And you see here that at that time, we would have expected to see 0.36 such alerts from background. So it could be that this is also only background, and you would expect this about once in 14 years. So because it's so rare, we decided that we will certainly have a look to see whether there are any sources there, and we then triggered follow-up. So here's the timeline. Unfortunately for this alert, our automatic client wasn't working. So there was a human in the loop. So therefore it was 22 hours before we could trigger. But usually this would only be 30 seconds. And we have had optical observations. The master telescopes were the first to observe very quickly. And then also LCO and Assassin observed later when it got dark in their locations. And we triggered the Swift XRT. And also we were very lucky because only 100 seconds after the alert, the Swift BAT, so the hard X-ray telescope, observed the location by chance. And then we also have gamma ray observations. So there's the Hawk Observatory in Mexico, which detects extremely high energy gamma rays. And they started to observe a few minutes before the alert and for the next 8 hours. And then Fermi observed 30 minutes later. And Veritas also started to observe, but they had to wait for the full moon to be fainter. So they only observed 1 week later. And just as a reminder, these are the sources we are looking for. And unfortunately, we didn't find very convincing source. And here are some examples of the data we took. So this is by the Swift X-ray telescope, and the error circle is 1 degree. So they had to do more than 30 pointings to cover the 50% error circle. And they found 6 sources. One of them is the blazer, but it's rather faint at that time. And then many of them are stars. And then there was one unknown source, which also faded away afterwards. But it faded too slowly for a GRB. And also we didn't find any variability at other wavelengths. So we think that this could maybe be either a stellar flare or maybe a very distant AGN. And this is also, it's the faintest source we've detected in X-rays, and therefore we thought that it's probably unrelated. And yeah, then we compare the limits we have to detect the GRBs. So here the two bands contain 80% of all GRBs detected by SWIFT. So the brightest 10% are above and the faintest 10% are below. But yeah, a typical GRB would have this light curve. So red is for the Bird Alert Telescope and blue is for the X-ray afterglow. And yeah, so then we can compare this to the limits we got. This is 100 seconds after the alert, and this is 22 hours later. And yeah, you see that we would have seen a very bright GRB up here, but a typical one could have been below our limits. So yeah, we can rule out a bright one, but not an average one. And yeah, just to show, so here the problem is that we were so late. I will just show you these are other follow-up observations that we did for different doublet alerts. So here, yeah, when we are a bit quicker, we can also rule out a usual GRB. Yeah, this plot shows you the same, but for the GRB optical afterglow. And here you see the optical limits we got by master and also by assassin. And yeah, also here we triggered too late to really see an optical afterglow of a usual GRB. And these are again the optical limits, but here we compare it to a supernova light curve. And so this shows you that yeah, we could have that a close-by supernova would have been detected easily. So yeah, with the master observations, we can rule out that a nearby supernova is present. And yeah, these are the gamma ray limits. They also didn't detect any sources, so we don't have indications for flaring AGNs. And there's one blazar inside the 90% error circle, but yeah, it wasn't detected here, so we don't know whether it was flaring at the time. Yes, so I would like to take the occasion to thank all collaborators that made this possible. So this is an overview of the limits we obtained. This is in the first 24 hours after the alert. And these are all observations we got within 14 days. And yeah, you see here that we have quite good coverage at many different wavelengths. But yeah, there was no likely source there. And yeah, you can look at all details in the paper. So here comes the outlook. Yeah, I also want to mention that now, since April last year, we have real-time alerts for very high energy track events that look like this. So in total, there are 2 different analyses to find those events. But in total, we expect to see 8 per year. And out of these 8, 3 are expected to be astrophysical. And then 5 are likely from background. And yeah, these are distributed publicly on this webpage. So anyone who's interested and has a telescope can do follow-up observations for these. And master is also doing this already. But yeah, here's one comparison I did. So for this plot, I assumed that the neutrino sources follow the star formation rate. This would be expected for supernovae and for GRBs also approximately. And then you can calculate at which distance a source would likely be located. And so if you detect one neutrino from the source, you can see here that 50% of the sources would be further away than redshift 1. And 50% would be closer. But redshift 0.1, there would only be a few percent of the sources from which you detect one single neutrino. And here I added sources from which you detect 2 or 3 neutrinos. And so if you have 2 neutrinos, the source is much closer. Here, the median redshift is 0.06, but this always depends on the number of sources you assume. But yeah, so for doublets, you would expect a nearby counterpart. So yeah, here's the comparison. For the multiplets, at the moment we trigger follow-up for 6 alerts per year, and we are not sure whether any of them are astrophysical. For the high energy singlets, it's 3 astrophysical out of 8. With the multiplets, you can find short transient sources, and they would be located nearby. Well, for the singlets, you can find any transient or steady source. You don't know anything about the duration, and it could be, but on average, the source will be far away. It will be quite distant. And yeah, so the multiplets are at the moment distributed privately, while the singlets are available on the internet for everyone. And so here's, for the end, my wish list, what kind of follow-up observations we would need to search for a source. So the typical error circle of the multiplets is 1 degree. Of the doublet, of the singlets, it can be a bit lower, maybe half a degree. But so you need a telescope with a large enough field of view. And yeah, you see here that for the Swift XRT, this is difficult. They have to observe many times. But for master, it works very nicely. Then we need reference images to know which of the sources are transient. And also, yeah, we would need quick follow-up, either to detect an optical afterglow, which you see here, but also to find out if we see a supernova, whether it was already present at the time when the neutrinos arrived or not. So yeah, the significance of a supernova detection depends on how well you can determine the explosion date. Then yeah, we need deep observations, especially for the singlets, because yeah, the sources can be very far away. And also, yeah, we need follow-up resources. Here's one example. This was a candidate which we found with the PTF telescope. And then later we got the spectrum, and unfortunately this one turned out to be a 1A supernova. So in this case, it's not interesting for us. But yeah, whenever we find something, we need more information to see whether it could be a neutrino source. Yeah, so this is my summary. IceCube can detect neutrinos starting from 100 GeV up to PeV ranges. We can now provide a real-time alert within about a minute. And we have several follow-up programs. I now only talked about the optical and X-ray one, but there's a different analysis where very high energy gamma ray telescopes are triggered. But yeah, so we've tested the system in the recent years. But yeah, so far we don't have evidence for short transient, and this triplet we detected could be from background. And yeah, we didn't find a very likely counterpart to it. Yeah, thank you.
Please.
Can I just ask about the track when you showed the little dots, coloured dots and so on? You said they're colour-coded for time, but each of those little points, are they individual triggers in each detector in a line? So, is that right?
Yes, exactly. So
So
here,
what's the sizing of them? Some look bigger and some look smaller.
yeah, the size is the number of photons
The number of photons.
detected by this photomultiplier.
So I was a bit puzzled because this is a Cherenkov shower in the detector, right?
Yes.
So is it expected to expand along the track?
So this is a neon track, and yeah, you see here the red line, and then yeah, as you said, the light expands from the track, but at the same time the particle moves through the detector.
So it's
Close to the track we see light first,
Right,
and
so
we see more light and further away.
So as it's progressing along, it's producing these.
Yes.
detections.
Exactly. So this one, yeah, came from below and then moved through here.
Right.
Okay, next question, Alexander.
What energy corresponds registered events between transients if you put the source on this boundary? What energy? From flux?
Yes, at redshift 1,
Yes.
you say?
What energy?
Yeah, I honestly don't know. So there are models for the GRBs.
What energy corresponds your transients between transients if you put the source on
Yeah, in
that
this
He asked you what luminosity, triplet,
Yes.
not proportional energy, integrated from time.
Yes, so I think
Multiplied per square.
so. There are models predicting the neutrino flux for supernovae, and there you would only find really close by 1. So the energy of a supernova would, I think, only be maybe 10 megaparsecs away.
He means
Yes.
that you see the flux of neutrino, okay?
So
You see some energy,
Yes.
and you can integrate it from the sphere 4p square to the flux. What is the energy flux?
So I don't know the
For
flux
redshift
of one source. I don't know the number.
Они видят одно нейтрино, они ничего не могут сказать об энергии, а потом...
The problem
Ну,
with
три видят случайно.
the problem with supernova then
Владимир Михайлович занимал. Владимир Михайлович, вы вопрос хотели задать. Короткий вопрос, короткий ответ.
First of all, thank you very much for your private alert for this triplet. This very important event in the neutrino astronomy. Maybe in future was the first beginning of the extra galaxy astronomy between optical and neutrino. And I would like to stress that the supernova name not very not very bad candidate for the neutrino, because 1% of supernova can be produced as a strong, have the very, very strong rotational and close to the neutron stars and black hole, and can be created the jet 1%. I will present this idea in my talk today.
Yeah, that would be interesting.
Okay, it's just Sergey Ivanovich.
I just wish to mention that standard supernova has very soft neutrinos, so you need something very unusual like a jet, extremely powerful, and I don't know actually if you can reach those PeV neutrinos in any of those jets. But they are, you know,
same as gamma ray bursts.
some physicists, they already computed, and I given it to you the references, probably, to Bykov and others, not supernova itself, but they found the candidate of supernova remnant interacting with strong wind in very efficient acceleration. So there are some physical models, but I don't know why they so rare events. But anyway, have you looked into
Yes,
that?
yes, I looked at the reference.
Okay. So in principle, it may be very nearby in our galaxy, but produced in a collision of shocks.
David, do you want to ask a question?
I just wanted to ask
Short
whether,
question.
yeah,
Short
whether
answer.
there's, you're checking in Hess to see if there are TV gamma rays produced at the
So,
same time.
so not for all alerts, but so there is a gamma ray follow-up program, and they have a list of AGNs that are known to have flares. And if they detect a certain number of neutrinos within several weeks from those telescopes, they trigger, at the moment, only Magic and Veritas, but yeah, we are planning to work with Hess also. And I think they've observed maybe 10 events so far.
We have to go on. Thank you. Let us thank speaker again. Next speaker is Dr. Zaborov. 25 minutes for talk and 5 minutes for questions.
Okay, so this is going to be about ANTARES and the follow-up of neutrino alerts. And I'm giving this talk for Damian Dornick, who was invited, but who couldn't come due to overlap with other meetings. Okay, and this is a list of people involved in this follow-up program. As you see, I'm not actually on the list, but I'll try to present the slides of produced by Damian. So this is just an introduction, since Nora gave us a good introduction. I think I'm gonna spend just a few seconds here. So as you know, neutrino are produced by a variety of astrophysical sources, or sources outside of the solar system. And ANTARES is working in the energy range here, in the GeV and TeV range, where atmospheric muons or atmospheric neutrinos dominate the fluxes. And the astrophysics fluxes, like from non-thermal processes, they are expected also in the TeV range to be most easily detectable, as you heard from the previous talk. So, and because these fluxes are very low, we need very large detectors to detect them, such as IceCube and ANTARES. It is important to use all available messengers to study those sources. And the specifics of neutrino is that it's very weakly interacting, so it can carry information from inside of very dense objects, and this signal can propagate also through dense envelopes and along all the interstellar matter and gas, and reach the Earth. But this also means that it's very difficult to detect these neutrinos, and this is why the usual way of detecting them is actually by looking through the Earth. So the neutrino will propagate through the Earth without interacting, and then you would see downwards and see the tracks coming out and moving upwards. This is at least the standard way of working in the GeV and TeV range. For PV neutrinos, the Earth becomes already not enough transparent, so you also look for down or side events, downwards or side going. Okay. Now let's go to ANTARES. So this is, you probably saw this picture many times. This is artist's view of ANTARES. It's just like IceCube, but in the Mediterranean water. The seawater is used as a Cherenkov radiator and also a target for neutrino interactions. Here we also use photomultiplier tubes like IceCube. These tubes, however, are arranged in a slightly different way. We use triplets of tubes, 3 tubes per story, and 25 story per line, and you have 12 lines, 12 detector lines. So, and all this is located 40 kilometers offshore Toulon, offshore France, and at the depth of 2,400 meters. And this experiment has been in operation for about 10 years. So just a few numbers about ANTARES. ANTARES has detected about 11,000 neutrinos since the beginning of its operation. Typical angular resolution is about 0.3 degree, and effective area reaches full efficiency at about few TeV, and the instrument is sensitive to neutrinos starting from 20 GeV. This map is not an ANTARES sky map. This is just some gamma ray map where we show the visibility of the sky by ANTARES. So here there is a gray spot which we do not absorb because we want to look through the Earth, so we do not see what's coming from above. But because of a 24-hour rotation of the Earth, we basically go through a large portion of the sky, about 3/4 of the sky, and we have the view of this part of the sky every 24 hours. So a bit more about angular resolution, as you heard from the previous speaker. There are track-like events and cascade-like events, similarly to IceCube. This is how we classify events. So the muon-neutrino charge current events are considered track-like because they have a very long muon track. So muon track can be many kilometers long if it's high energy, while all other events like neutral current events or charge current muon-neutrino or electron-neutrino and so on, they all produce something which looks like a cascade, a more compact event. We call them, all of them, cascade. For these events, the angular resolution is much worse. It's about 3 degrees, but this is much better than IceCube. And the reason for this is that light scattering in the seawater is much less, so we have a much clearer pictures of the chunk of light. So we can get a much better angular resolution than IceCube. So here is a sky map obtained by ANTARES after all these years of operation. The actual neutrino events are blue dots here. So the final result is that there is no particular clustering in all these blue points. So the whole picture is consistent with just a flat background of atmospheric neutrinos. There are some interesting regions which were examined, particularly like AGNs and so on. We call them candidate sources. So for these candidate sources, we have a special list of these sources with an upper limit for the flux for each source. So which, or you can also express this as a function of declination. Then for each declination band, you have some value for the upper limit. So this is shown here in comparison with, so this ANTARES result is, I think, the red line, and then this is compared with the blue line from IceCube. As you see, IceCube is much more sensitive than ANTARES, at least if you assume this E2-2 spectrum, which is kind of a standard assumption for astrophysics fluxes. So IceCube is much better than ANTARES for the range of declinations, which is visible for IceCube through the Earth, but for the range of declinations where IceCube has to look for downward going neutrinos, then they have this background from atmospheric neutrinos, and therefore their sensitivity gets worse. And in this range, ANTARES provides still the best upper limits on neutrino fluxes. Right, so of course we can also look for transients. So that previous slide was just for steady sources, for steady point-like sources. We can also look for transients, which of course has been done, a variety of transients like AGN flares, GRBs. But now this conference is about online follow-up. So let's talk about follow-up here. This slide shows a general scheme for for follow-ups of Antares neutrino alerts. So we have some online analysis running. The data are reconstructed in real time. And if there is something interesting, like very high energy neutrino or doublets, then the scheme is to send out an alert to various facilities, including master. And then we also have the capacity to receive alerts from things like GCN and react to these alerts, possibly producing another outgoing alert. So so far, Antares produced alerts about of 3 different types. One type is the doublets. However, the chance of a doublet from random coincidence is very small because of a lower neutrino count rate compared to IceCube. So actually, if I understand correctly, this never actually happened. So there was no doublet so far. And most of the alerts you're probably receiving are of the other 2 types. Either it's single high energy neutrinos. High energy means 7 TeV or so, or higher energy. And we send out these alerts, around 15 alerts per year. And then we also have a list of local galaxies, which I think are 20 megaparsec, for which we have a reduced threshold for sending out the alerts. And this reduced threshold corresponds to 1 TeV. So you can have some extra number of alerts from these directions. And the online analysis is pretty fast. It can send alerts about 5 seconds after the neutrino has been detected. This is just a map with showing dots for the facilities which receive our alerts, such as master, some other optical robotic telescopes, then HESS, gamma ray telescope in Namibia, then Swift, and also HAWK, which was mentioned during the previous talk. HAWK actually has no mechanical part to move, so they do not actually need the alert, but if you send them an alert, they can analyze their data and tell you what they see. Right, so I think this map shows there's a percentage of time when you can get a prompt follow-up of an Antares alert on the map of the world, and it turns out the best positions for observing Antares, for following up on Antares alerts in optical are somewhere near Australia, which is not surprising because Antares is in Europe and it looks through the Earth. So if you want to see the same place in optical, you probably want to be somewhere in Australia. But also facilities which are in South Africa or in Siberia have a fairly good percentage of getting prompt follow-up. So they are far enough from Europe to get a good percentage. So these are how the alerts are distributed on the sky maps in galactic coordinates, I guess. So blue, black for prompt and red for long-term follow-ups. And I think this is compared with Antares visibility here. 256 alerts has been sent to robotic telescopes. Most of them have been followed by at least one, and at least half of them have been analyzed already. 13 has been sent to Swift. The reason for sending less alerts is just because they asked for less alerts. The agreement was for less alerts, so we only sent the best, the most interesting alerts to them. Same for MWA, and HESS only asked for very few alerts, so they received 2 alerts. Here is the observation strategy. For different telescope systems, the observation strategy is slightly different. I guess you probably know this better than myself, so I'm gonna stop here for long. The prompt observations are mainly to address the question of GRB afterglow, which has a typical time scale of minutes to hours, and then longer term follow-up covers time scale typical for supernova explosions. So this is a histogram showing which facilities of master contribute how much to the follow-up of ANTARES alerts. It turns out that South African facility seems to be most frequently used for these follow-ups, but also all other master facilities contribute. This shows the days after the alert, which it takes to get the follow-up. So versus the NJD, this is just the time when the alert happened, and this is how long it took to get on source. There's a number of events which were followed within a minute, and there are many more which were followed within 24 hours. So this looks pretty good. So this shows the limiting magnitude. It appears to be about 18 for these follow-ups, and it's pretty stable in time. Now let's get to the results. The results for optical are here on top of the slide. Most of these follow-up alerts have been analyzed, and there was no particular transient candidate found, no solid candidate. So what we get is upper limits. And here these upper limits on the optical magnitude are compared to light curves of typical GRBs. And on this plot, you can notice that basically, if all these events were typical GRBs, we would probably see many of them. So this actually places constraints on the nature of these individual neutrinos, which correspond to these alerts. This is an interesting physics results. Similarly, for X-rays, we have limits which are actually lower than the typical GRB afterglow curve, and which means that we can actually constrain the nature of these neutrinos, and we know that these are not typical GRBs, or at least not GRBs at typical distance of where these other curves were measured. So these are also interesting results. Now a few extra words about one specific alert, which was a bit special. It's from September 1st, 2015. Funny enough, this alert happened in a position on the sky which is close to the star called ANTARES, just like our experiment. So this alert has been sent and followed by Swift and master. And so Swift detected some transients quite near this alert from ANTARES. However, it was later found that this transient was a cataclysmic variable, and probably is not, therefore it's probably not related in any way to the ANTARES alert. It was just a random coincidence. However, this alert generated a lot of follow-ups and lots of activity in the ATALs and follow-ups in optical, X-ray, radio, and gamma ray. So this was an interesting exercise, and this will lead to publication. Hopefully, there's a publication in preparation of this birth or this event. Another paper in preparation is about long-term follow-up. Perhaps some of you are already involved in this. If not, then maybe you should be involved. Yeah, so 177 alerts have been analyzed, and then this paper will, I presume, it will include analysis of these alerts. All right, so then one more slide about radio follow-up. There was a few alerts followed by NWA. So far, only 2 were analyzed. I think these were from offline analysis, and nothing particular interesting was found. In the gamma ray band, the high energy gamma rays has followed up on this ANTARES September 1st event. I didn't find anything interesting. So now, what's next? Next is KM3net. ANTARES will be decommissioned, perhaps on the time scale of a year from now. And the next generation experiment is going to be KM3net. There are many important technological advances which makes KM3net better than ANTARES. In particular, have new design for the story. Instead of 3 large photomultiplier tubes, you have 1 glass sphere with many, with 31 small tubes. And actually, this sphere is about as sensitive as this whole story here. But it doesn't. You don't need any of this titanium structure or electronics container. Everything is integrated inside 1 sphere. This gives you a much more compact design. And then instead of bulky cables, we have this very tiny Kevlar strings and also oil-filled tube with all the optic fibers and electrical conductors. But the scheme remains the same. The principle of operation, you get current of light from neutrinos in the sea. This collaboration includes many countries. One of them is Russia, actually, and Moscow State University is an associate member of this collaboration with a group of Evgeny Shirokov. So KM3net is not a single detector, it's actually 2 different detectors. One near the French coast, very close to the ANTARES site, it's called ORCA. This is only for, primarily for neutrino oscillation studies, namely for the determination of the ordering of the neutrino masses. The second facility is ARCA, which is a cubic kilometer detector for astrophysics. It's being built near Sicily, on the Italian coast. The instrumented volume of ARCA will be similar to IceCube or slightly bigger than IceCube. And this is much bigger than ANTARES, which is only 20 megaton, while ARCA will be 1 gigaton. And this the oscillation experiment of KM3net, the ORCA, will be about 6 megaton. But the oscillation part is sensitive to neutrino starting from 3G, which is important for the mass hierarchy measurement, while this big experiment is for mainly for TV and PV neutrinos. So the angular resolution expected for KM3net is shown on this plot is going to be 0.1 degree, which is much better than IceCube, which will help with to identify the sources once they are found. And of course, it also helps with sensitivity to point sources. And this is for muon tracks, it's 0.1 degree, and for cascades, it's going to be about 1.5 degree as compared to 10 or 30 degree for IceCube. So this is much better. Again, this is thanks to better optical quality of the seawater compared to ice. And this is projected sensitivity. KM3net will be more sensitive than IceCube and will cover a larger range of declinations. This is a picture of one of the actual CAN3net lines in a test facility. So as you see, these things are actually exist, and they are being built at a steady pace. And deployment is also starting. 3 lines have already been deployed, and many more will be coming hopefully soon. The deployment uses so-called deployment vehicles, which is a kind of a sphere like this, where you pack all these small or all these glass spheres, which house photomultiplier tubes. So you have a compact structure. You can put several of these structures on the deck of a ship and deploy them in one trip, which simplifies the deployment, makes it cheaper and faster. And then this thing will unfurl itself in the sea, and it becomes a string. This actually works. This has been tested with a few lines already. So CAN3net is coming, and we hope that Master will continue to work with us, following up our alerts, and also will continue towards CAN3net. Master is an essential part of the multi-wavelength follow-up program of ANTARES. So we hope we can continue our collaboration successfully in the future. Thank you.
Thank you. Quite a lot of time for questions, but if there are, anyway, we have 1-2 questions.
Черновила только пока.
Please,
You mentioned that the angular resolution achieved by ANTARES is much better than angular resolution achieved by IceCube.
It's because of light scattering. In the ice, you have lots of impurities which scatters the light, and therefore you get a fuzzy picture of the chunk of radiation cones. So it's not as clear as you can get in clear water.
Okay. Second question: you mentioned some events related to nearest galaxies or nearby galaxies.
Oh, there are. I'm actually not sure how they selected those galaxies. I presume they just took a catalog of all local galaxies, assuming maybe there are some supernovas happening there. I don't know. It's just a list, but we don't detect any significant signal from this sample. It's just a way to look at these galaxies more closely, so you have a little bit more alerts, smaller, lower threshold for alerting the other telescopes if there is anything from these directions.
Last question. The last question.
Today, Nature published a paper about ANTARES' strange atmosphere, its observation in carbon monoxide climate. Do you know it?
You mean the ANTARES star? Oh, okay. I don't know.
Okay, let us take the speaker again. The last speaker before coffee break, Oleg Gress, Master Investigation of ANTARES IceCube programs.
Здесь.
More detailed in other books, master investigations of regional localizations in very and ultra high energy neutrino sources. This idea of multi-message astronomy, I think you hear before me, and I don't talk about. this multi-messenger context about ideas, neutrino direction, discovery of node types. Start. Our objectives. Our objectives: search for optical transient in the master database using neutrino alert events. By area, 2 error box for ANTARES alerts and 1 error box for IceCube alerts. By time, all time before and after time alerts. By type of optical flashes, by specially coincidences. Master telescope observes fast transfer to each other of neutrino events for a long time with a set of long exposure times with the maximum possible magnitude. As you can see, as example, observation time is about 1 month, typically ANTARES event. Exposure time a few hours, and limit from 16 to 20 magnitudes, some magnitudes. This is example of coverage areas by master survey modes for IAC telescope and SAO telescope. The methods of searching for optical transients in the master database are the viewing of optical candidates, discovery or supposed to be discovery, careful study of each candidate, analysis of image, info search in the astronomical catalogs, Wizard, Simbad, OSC, etc., and recording of available information. The final format of search results consists of ANTARES alert information, visibility, azimuth and zenith angles for objects, sun, moon, for each observatory at alert time, and very important information, viewing time of this database for further in future analysis, number of detected optical transient after and before alerts time, and all available information about each detected optical transient. So, sky map of arrival direction of neutrino even in galactic coordinates. ANTARES neutrino is magenta color, and red color is IceCube among neutrino. We can compare the neutrino events and optical transient, and so statistical research field. For this during time 2015 to 2017 May, we have 109 ANTARES alerts and 134 associated optical transient. Inside 3-degree error box table is given the classification of this optical transient by type optical flash, and right you can see the presentation in the circle diagram. Most optical transient is UJ type, and about 25% is unknown variables. These variables go from 2016 years, about 20. IceCube neutrino. We have from 2016 to 2017 years about 12 IceCube alerts, and was found only 4 optical transient inside individual error box. If we accept very strange neutrino event with a very big error box, about 8 degrees. Classification is table. and all optical transient was before LED times, and deviation about 1-2 degree. Deviation coordinate optical transient from neutrino arrival direction. Only one is event, less more normal Gaia. In this search, we use two ideas. First idea is search the hidden pulsar among the neutrino and optical transient candidates. As you hear, maybe, and as Professor Riponov said, some cataclysmic variable can be sometimes produce high energy neutrino. White dwarf must be invisible, and maybe it had detected during neutrino production moments. The optical transient will be appear after a long time, after neutrino detection. Result such search for UJS Nova among the neutrino events was found 10 optical transient. Among these, 4 discovered by Master, 6 optical transient was discovered known optical transient, and only you can see yellow color inside Yellow box, ANTARES Yellow box. Very important question: how realistic is the coincidences? Estimation the random coincidences number of neutrinos and optical transients is consistent with the observed number of coincidences. It is pretty, sorry, not very optimistic result. While idea 2, search for optical transient in close directed ANTARES neutrinos. Was found one event with 4 alerts with 3 error box, 6 events with 2 alerts, and a coincidence for ANTARES and IceCube neutrino events. Was found 1 event with 2 alerts with 2 error box. Spatially coincident events of neutrino alerts and working number in these events. This 4-fold number 1, 4-fold number 2-fold number 1, etc. You can see this a galactic plan and light yellow supergalactic. Very interesting event with 4-fold ANTARES neutrino alerts. When neutrino go in 15th, 2 in 16th year, and 17th. Zenith angle very good, optical transient is absent. Possible neutrino candidate, Cypher Galaxy MID, and another available. At another look from other side about average position this event, we can find that Zakharov and outburst about 1 month after the first neutrino alert. And we have 6 events in case 2-fold coincidences. Number 3, optical transient is absent. Number 4 is absent. A very strange optical flash from young stellar object in 2017 years. Very good zenith angle for neutrino. And most interesting event is optical flash from Glazar between alerts in 2015 and 16. More detailed information for this optical flash Glazar. Glazar is very active in wide electromagnetic range. And first neutrino event is deviation from optical about 0.6 degree, but second neutrino more 4 times. Optical transient associated with ANTARES and IceCube neutrino alerts, two events. ANTARES IceCube, two ANTARES, one IceCube neutrino. In 2016 was the optical flash was at third master hour, 24 minutes after the ANTARES alert from a known source assassin. More detailed information. We have deviation from the alert direction about 2 degrees, very big value. Maybe this repeated optical flash. Summary information in spatial equation neutrino alerts this table contains. Red color indicates closer to 1 error box plus 30%. So for search in astronomical database was made to study the number of active star objects and the search for possible search of neutrino and associated optical transients. Symbolic object, ARIES, number ARIES, short abbreviature of symbol, one case when candidates Blazar and optical flash was Blazar. Summary. 6 optical flash from known sources, 2 optical flares from unknown weak sources, and 8 transient was discovered by master. Possible candidate may be Blazar, Zakharov ultra-type, supernova, UV-CT version, уже subtype, and very pointed in this situation question, how exactly does a space gun shoot? Result in the table. Only in the case F for fault coincidence neutrino within 3 error box, they observed more random. This is only one neutrino, event F for neutrino. Conclusion was made. Selection of optical transient, database F, this transient analysis classification, search for possible hidden pulsar, search among two fault, and search in astronomical database. Thank you very much.
I would like to some small edit to your talk and previous talk. I would like to show the ANTARES alert observation from master. We presented to ANTARES several times, but people don't take. But you see this very nice picture. The best picture is neutrino astronomy. You see, here green the neutrino alert, ANTARES alert. On the left corner, there is a star ANTARES, this color image, master color image from South Africa. That is one of the nearest pulsar in the galaxy, millisecond pulsar, binary millisecond pulsar, maybe this planet. And this globular cluster, and here's the X-ray, Swift X-ray candidate. Okay, so I presented to ANTARES people and to yours talk.
Actually, it wasn't my talk. In my talk, there was a picture from master. It was as a background.
But black and white. Okay. No, this. That is so.
Okay, they want to ask.
Вы с вами не продадите, понимаете?
Yes, you wanted to ask.
Yeah, I was wondering about the association between dwarf novae and some of these neutrino events, because I don't really understand what the physical connection could be. What is the process you think would produce neutrinos in a cataclysmic variable?
The next talk. Here.
I mean, I just don't see why it's just not chance coincidence, because there are dwarf novae going off all the time. that happen to be inside these error circles. So the physical connection between them I don't see.
Maybe I agree, but and single neutrino is very important. But if you must have the source from neutrino source as supernova 1987.
Sure. Yeah.
Several neutrino during short
but,
time.
but there we understand the physics. It's what's going
This
on.
question not for him. This is another talk. Next talk.
Well, but he
Attempt
presented
to paint in this.
Yes, it seems to me again, this picture is very uncertain still. It's something like gamma ray burst before Beppe size. So because it's error bars is too big. I mean, because for astronomy it's too big to
but he calculated
certain.
He calculated probability of the.
Yes, but probability. Joseph Weber also calculated probability.
No.
They were very small.
We must believe.
Okay, let us speak again now. We
Давайте. Алло? Лисенок, через 2-3 минуты перезвони, хорошо? Вы говорить будете по-русски? Да. А по-английски не можете? Ну, не готово. Вот это Куба.
Из одного пакетика достать.
Не знаю, может кто-то устал.
На пароход не надо брать, это опасно.
Кого не надо? На пароход. Уплочено. Извини, уплочено. Что?
И набрать тех, кто не опаздывает.
А нет, к сожалению.
Okay. Okay. Now we will start our session. Second morning session. First speaker is Musabi Boliev. We will do two talks now. 15 minutes for talk and 5 minutes for question. Okay, excuse me. We started our...
Я буду говорить по-русски. Собственно, мы пока еще не участвуем в этих мультимессенджер проектах, но есть уже одной ногой будем участвовать. Но наша установка Максанский подземный сцинтилляционный телескоп, значит, вот можно видеть, он по сравнению с современными телескопами детекторами маленький. Значит, вот здесь закралась одна ошибка. Значит, при некоторых траекториях точность может быть и выше, чем 1,5, но средняя точность 2,5 градуса. 2,5 градуса. Значит, внешний вид телескопа. Вот это прямоугольный параллелепипед с 4 горизонтальными слоями и 4 вертикальными. Значит, вот демонстрация метода регистрации. Тут способа регистрации тут представлено первое событие, которое было зарегистрировано на этой установке в 1978 году. Было первое нейтриное событие. То есть нейтрино образуется в атмосфере на обратной стороне Земли, проходит через Землю, где-то в районе установки взаимодействует и порождает мион, который мы, соответственно, и регистрируем. Надо сразу сказать, конечно, что как и все остальные установки в мире, которые говорят о регистрации нейтрино, мы регистрируем в основном атмосферные нейтрино, как и все. Но любой из этих нейтрино может оказаться не атмосферным, а галактического или внегалактического происхождения. Значит, вот это мы для демонстрации, как наша установка работает. То есть это единственная установка, которая работает на протяжении такого долгого количества времени и очень в хорошем состоянии. Хотя все электроника и все прочее, естественно, устаревает, но вот эта красная линия, это сколько времени было бы, если бы не было ни мертвого времени, ни остановок, ничего. А это реальное. Любое время, оно очень прилично. А это количество нейтринных событий за все время набранные. Значит, ну и тут вот эти цифры, которые здесь представляются, это живое время вот такое, количество ионных нейтрино из нижней полусферы. И еще мы регистрируем как бы нейтринные события в горизонтальном направлении, но здесь могут быть примесь рассеянных мионов. То есть реально стопроцентными нейтринными событиями являются вот эти события. Значит, здесь я представил, значит, на самом деле, какую часть звездного неба мы видим. Вот здесь время, живое время, а здесь склонение. И вот эта область на нашей установке вообще не наблюдаема. Вот. Ну, эти тоже области имеют малое живое время, хотя наблюдается, то есть они то под горизонтом, то над горизонтом, поэтому, в общем, вот такое распределение. А это для наглядности, вот какую часть звездного неба наша установка наблюдает. Значит, это в звездных координатах, это в галактических. Вот эта часть для нас слепая. Ну и для как бы результата мы посчитали ограничение на поток от некоторых объектов, ну, популярных объектов звездного неба. Значит, вот эти числа, ну, если представляет интерес, можете... Да. Так, дальше я все быстро закончу. Дальше мы, естественно, наши нейтринные события пытаемся сравнивать с всякими такими явлениями. В том числе вот это явление регистрации гравитационной волны. И у нас, есть ли у нас события, которые совпадают по времени и по координатам?
А это энергия нейтрино, которую вы фиксируете.
Да.
До скольки неф?
Да, там вот эта часть не ограничена, конечно, вот ограничена вот эта часть. Значит, и ну, сделали некие ограничения на ожидаемый поток, осветимость этого объекта. Ну, на самом деле вы знаете, что это не точечный, представляется не точечным объектом, а протяженным таким объектом. Вот сейчас на следующей картинке будет это вот некая такая штука. Вот мы дали ограничения. Хотя на самом деле вы понимаете, что это игра. В том смысле, что объект находится очень далеко. Установка небольшая. Естественно, поток будет совершенно невидимый. Должен быть, по идее. Или должно там возникать какое-то невероятное количество нейтрино. Хотя там, возможно, и не появляется нейтрино. Этого никто не может точно сказать. Ну и вот по всем этим событиям, собственно говоря, я закончил.
Сначала по-русски, очень приятно с вами познакомиться. Это наши будущие коллеги. What about the time of the reduction of the triggers time?
Значит, точность, значит, для события 0,2 миллисекунды.
Да, через сколько времени вы можете передавать информацию?
Значит, реально мы можем передавать через, скажем, пару секунд, через секунду. Но на настоящий момент мы можем в течение, там, скажем, 6-7 минут, вот в данный конкретный момент, да. А реально мы можем в течение секунды,
Значит,
двух...
надо выдавать в течение секунды.
Ну, для реализации этого надо нам кое-какие изменения, модернизацию в онлайн-систему ввести. Ну, в принципе, это реально. Реально.
Other questions, please.
What is the exact position of the unit corresponding, assuming they correspond to the gravitational wave detection? Какое точное положение, предположение, с чем совпадает на небесной сфере вот это положение? С большим Магеллановым облаком?
Нет, ни с чем.
Нет, оно ниже. Сейчас я найду. Вот оно. Ага, значит, Магеллановое облако, наверное, примерно...
Минус 60.
Да,
7,
да. Где-то, да, вот здесь. Оно не полностью совпадает. Оно, видите, как такая...
Это гравитационно-волновое. Звезда-то ваша.
Нет, нету событий.
Это нет. Это некий центр, вес.
Это были когда-то.
Они, да. Вот конкретный... Вот черт. Тут не 50, 5 days. Не 57, а 5 в течение 5 дней.
А если 57?
Ну,
там есть попадавшие?
Вот этого я не смотрел, но...
Ну, хорошо. Ну, это документ уже, все.
Да, 5 days.
Okay, if there are no other questions. Yes.
No, sure, yes, that is a new collaborator with Master, and maybe after several months we publish a first result for our collaboration. So South Africa and Argentinian Master can be included in this cooperation.
Okay, let us thank speaker. And speaker is Rabinovich-Ishmuhametova. 15 minutes for talk and 5 minutes for questions.
Hello for everyone. My name is Ishmuhametova and I'm a student of Irkutsk State University. And today I want to tell you about the search of astrophysical sources in IceCube's error boxes. and a possible new mechanism. I want to note that these error boxes were investigated in the optical range first time. So the sources of ultra-high energy neutrinos are traditionally considered to be supernova, active nuclei of galaxies, gamma ray burst, Fermi bubbles, and double star. However, last year, the new class of object was discovered, a pulsar on a white dwarf. In the known system that contains a white dwarf and a red dwarf are Scorpio. You can see the period of this pulsar is 1.97 minutes. And it has a second harmonic. Master telescopes check the object for rapid variability. But I should note that it's interesting that this pulsar is located near the coordinates of one of the error boxes of IceCube. You can see the coordinates here. So on the first image, you can see depends of magnitude of time, and you can see second harmonic, and this is Fourier spectrum for the pulsar of white dwarf, and you can see that the main periods are considered with periods which note in last image in nature. But we have a question: can such a pulsar be a source of ultra-high energy neutrinos? Let us estimate the energy of particles accelerated by such pulsar. We assume that the acceleration of relativistic particles occurs near the poles where electric and magnetic fields are parallel. And we have these results: 1.5, 10 to 16. It's the upper limit of the energy of a relativistic particle which accelerated in this pulsar. Of course, in the real system, acceleration occurs in a small gap at the poles, but the upper limit is so high that we think that there are no fundamental limitation to production of ultra-high energy neutrinos. But if it's right, could IceCube registrate them, these particles? And we carried out calculation of relativistic particle stream from the white dwarf in the area of 100 parsecs. It corresponds to a particle stream from a quasar. So this means that IceCube can be registered this particle, and that neutrinos from such source could be detected. We also observe all error boxes of IceCube Observatory in optical range. The number is 13 error boxes are left, and we found 82 transients, among which we found 27 quasars and 25 cataclysmic variables, one of which stars, and I'm sorry, but others I can't be classified. So it's all masters open it. There are 79 supernova in error boxes during the year before each of error boxes, or each of others, sorry. So it's too many, and we can't recognize the real source between this supernova, if it would be, because there are no temporal correlation. In conclusion, I would like to summarize my results. As I said, it is the first observation of neutrino error boxes in optical range. And results of observation allow us to state the new hypothesis about cataclysmic variables might be sources of ultra-high energy neutrino. We carried out calculation of estimate energy of particles, which are accelerated by pulsar on a white dwarf, and we carried out calculation stream of particles from the white dwarf. And now we are working on methodology for determining the period object, short variables, which master removes. So it was my first experience in such conference. Thank you, and happy birthday, master.
Time for questions or remarks or suggestions.
In the case of ARSCO, the white dwarf is highly magnetic, far more so than normal cataclysmic variables. So while I don't quite understand the process that gives rise to neutrinos, I know there's particle acceleration going on in the system, and maybe you can say what is the process that produces the neutrinos. But in the normal CVs, which are low field systems, which are dominated by accretion disks, I still don't understand what is the physical process that you're advocating that will produce neutrinos from dwarf novae.
Можно я скажу по-русски, а кто-нибудь?
Скажи по-русски, я переведу.
Ну, про джет.
Скажи по-русски.
Процесс рождения нейтрино таков, что этот пульсар, когда джет попадает в соседнюю красного карлика, да, и проходя через это, он попадает в зону нашего видения. Только в этом случае мы можем наблюдать нейтрино.
I would like to translate in some way. She said, we try to find sources of neutrino between cataclysmic because the system contains white dwarf and optical stars only. Because in some situation, cataclysmic variable, of course, can be white dwarf can be transition between the accretion and ejecting stars, which we show maybe 30 years ago, 40. In this institute, all people know this. Only last year in Nature was discovered first radio pulsar, as we predicted. And so we see in Nature, we see the real accelerator on white dwarf. That's very important for the people, because theory, no theory of pulsar now, no theory, no theoretical model which can be produced this real spectrum and real gamma X-ray optical spectrum. No model. I would, every pulsar conference, I ask it, please take the magnetic field and period and angle. Give me spectrum, nothing. So the model is unknown, but we know the upper limit, this absolute upper limit, and you see for the 100 seconds, we receive the PV energy of particle. This particle, you let's say, produced by pulsar, come to the optical companion. You understand? And by the nuclear neutrino baryon reaction produces the neutrino, relativistic particle, and optical baryon reaction produces neutrino only at this moment when the optical stars look to you. So you can observe a lot of white dwarfs with the optical without any neutrino. But in some very not often cases you can produce it, the paper in preparation.
The problem is, Vladimir, that the stars are not in a line like that. It's a high inclination system, and the beam does not sweep by the Earth.
So we not publish this result. We do not say that the radio pulsar was discovered 1 year ago is real producing neutrino. She said she is the observer. Donald Trump to observer. Observer must to say what she see on the sky. But really, of course, this may be another. But nature is, as usually say my teacher, academician Zildovich, the father in this room, he said very often that nature is more complicated than we can think about it.
But just to get back to the real question I was asking, is that ARSCO, this high magnetic field white dwarf pulsar, is the first one ever discovered, right? This is the first time it's ever been seen.
Yes, because there's only...
And there's no connection, really, between it and normal dwarf novae, because it's not accreting, it's very low field systems in dwarf novae. So I don't understand...
You do not understand astronomy. You see, you must... Okay, my question to you, what this pulsar was before discovery? What kind of variable star was before discovery? What?
Well, it was
Delta Scuti stars in catalog. You understand? Because stars. No.
What I'm trying to understand.
No. So we must fight all. Мы должны искать. Ну подождите. Мы должны искать все подозрительные объекты, в которых есть белые карлики, потому что этот пульсар 40 лет назад, в 70-м году, был объявлен Дельта Скути переменной звездой, не имеющей никакого отношения вообще ни к белым карликам, ни к чему. А оказался радиопульсар. Вот в каком смысле она и ищет.
So if you know some fundamental limited to this hypothesis, you should
I mean, we've been working on this system very intensively, doing polarimetry on it, and it's a very interesting
Delta Scuti has
and I do not disagree that particle acceleration is happening in this system. The synchrotron emission, it's dominated by non-thermal processes. It's an intriguing, very interesting object, but it's totally different to a dwarf novae. And that's what I was asking Vladimir, is what is the process in a normal dwarf novae that gives rise to neutrinos, that they could be neutrino sources? Because I don't understand.
No, I say, what What is the delta scuti? I repeat my question. The delta scuti, okay, no white dwarf.
You can't answer that question.
You don't answer.
To let us say followers.
Not scuti, not
But I
white
think
dwarf.
up at the conference dinner you will solve this issue. Please, Franco.
I have a comment. The nature, as I said, is compounded by a continuum evolution. And in my opinion, it is important to see the scenario machine introduced by Vladimir many years ago, in which you can have the evolution of each kind of sources, like, for instance, delta scuti, white dwarf, pulsar, etc. And maybe that inside this scenario machine, we can have answers about many, many problems, including this one.
Okay, do you have comment? Please.
I agree.
Okay. Okay, if there are no other questions, let us thank speaker again. It was, I think, it was a rather question. And the last talk of this morning session will be delivered by Musabi Boliev.
Это доклад будет, в общем, презентацию готовил другой человек.
Ответственность вам будет.
Да, я ее, тем более, что я его, да, значительно сократил и, может быть, испортил. Значит, значит, это регистрация нейтрино от коллапса звезд. Вот такая штука. Значит, это вы видите вообще, где это находится, под горой. И тут много, несколько установок, детекторов. А отдельности интеграционный телескоп вот здесь находится, под Аст. Дальше еще находится. Вот в Галле, Германии, вот детектор. И так далее. Это, следующую картинку вы уже видели. Значит, единственное, что тут вот для регистрации коллапсных событий все время использовался вот этот слой, этот и этот. Три, а остальная часть как антисовпадательная, как защита вообще, как защита от мионов и защита. То есть для коллапсных событий это нейтрино-электронные, которые, естественно, порождают электрон, и они дают сигнал только в одном счетчике, в одном маленьком счетчике. И поэтому нужно, чтобы на все установки требуется, чтобы одновременно сработал для вот коллапсного, регистрации коллапсного события, чтобы один счетчик только срабатывал на все установки. Вот это... Ага, я обратил внимание. Виноват. Ага. Значит, ну вот реакция какая используется. И потом, вот когда производится поиск коллапсного события, мы берем любой момент, когда сработал вот такой один счетчик, вот какой-то, и просматриваем 20 секунд. Сколько за это время вот таких одиночных счетчиков? Ну, есть какой-то фон, который где-то тут будет потом. Значит, если за 20 секунд сработало значительное количество, превышающее, естественно, у нас какой-то фон, то мы считаем, что зарегистрировано явление коллапса какой-то там звезды. Это вот ожидаемое количество и эффективность наших счетчиков. Это, допустим, вот какие предположения, вот это начинают вот такие предположения об энергии, полная энергия, которая нейтрино уносит. Значит, ну, это тут изображено, вообще-то говоря, фоновые явления для этого события, а может не только фоновые. То есть вот эти нейтрино, они могут создавать в счетчике изотопы нестабильные, которые потом распадаются и дают сигналы тоже. Эти все методы используются для вот, регистрации, для выявления увеличения потока электронных нейтрино. Значит, вот тут все почему-то задано вперед. Вот этот фонд, который мы имеем, список, собственно говоря, я думаю, вам это не интересно. Так. Это вот темп счета, если вот для фона, то есть у нас счетчики очень стабильно работают и шумят редко. Вот это вот для тех трех плоскостей, которые я говорил, вот это хитрость нарисовано, чтобы можно было и эту картинку показать, и это распределение. Вот 0,02 секунду, то есть в час два срабатывает. 0,02. Нет. За 100 секунд два срабатывания только счетчиков. То есть очень мало эффективно работает, не шумят. Опять же, это вот поведение этого дела для вас очень интересно. Вот это фон, как за весь период вел себя фон. Тоже вам не очень интересно.
А два срабатывания это настоящих или это вы имеете в виду, что два срабатывания?
Это, значит, это шум, в том числе и шум, и где-то вот этот список. Космический, ну, все сопутствующие работе, там мион может в щель проскочить и дать одно срабатывание, там внутри фэу может произойти какое-нибудь спонтанное срабатывание, то есть это вот фоновые. А для коллапсным событием будет считаться, если вот за вот эту 20 секунд, которые мы берем, это время, вообще говоря, эмиссии вот, взрывающей, ну, коллапс следующей звезды максимально. Да, 10 секунд и там плюс еще сколько-то. Вот за это время, если у вас будет много, если у нас много вот таких одиночных, то тогда мы уже начинаем о чем-то рассуждать. А так, вот это два это фон такой, шум. Белый шум или черный шум. Значит, это вот какие-то сопутствующие измерения. Тут можно на нашей установке были получены результаты по вот этому времени распада вот этого дела, энергии. Это все такие. Вот это у нас за много-много лет где-то тут было. Вот эти все фоновые события, и как они вот эти 20-секундные такие пакеты, сколько срабатываний, вот 6 штук, 7 штук, 8, 9 и все количества. Ну, это вот аппроксимация, это вот, сплошная линия, это ожидаемое количество для данного количества фоновых событий. Вот. И для вот это, вот когда 9 одиночных срабатываний за 20 секунд, оно очень редкое явление. вообще говоря, здесь вообще не наблюдается. Вот если мы увидим вот такое, то можно уверенно говорить, что где-то произошел коллапс. Это два метода. Это есть вот это 20-секундный от каждого отдельного события, плавно меняется, а есть метод еще 20 секунд закончились, с его конца еще 20 секунд смотрите. Если так смотрите, еще меньше этих событий. Собственно говоря, вот радиус, который, вот это интересно, более-менее, на котором мы можем увидеть коллапс.
Каких единиц?
А это в парсек, килопарсеках. Вот это.
Кило?
Да. Это килопарсеки.
Ну, то есть до Магеллановых такое.
Нет, до Магеллановых у нас будет k равно единице, и это будет ничто. То есть реально о чем-то можно начинать говорить, вот когда 6, тогда надо еще дополнительный анализ провести, и тогда может быть. То есть мы видим только нашу галактику. Это расстояние от Солнца. Расстояние от Солнца. Вот 23 килопарсека, мы чувствительны на 23 килопарсека. Коллапс, если в нашей галактике произойдет, то мы его разъясним. Правда, возможны такие случаи, когда не будет недоступен оптическая компонента. Для анализа таких событий мы совместно с LVD, например, проводим совместно анализ событий. Если у нас есть 6 событий, мы смотрим, есть ли у них в этот конкретный момент времени, есть ли у них события. Если они совпадают, то можно уже как-то о чем-то говорить. Единственное, что вот регистрация коллапсных событий не дает никаких координат вообще в направлении чего-то, и поэтому для ваших телескопов эта информация совершенно бесполезна. Спасибо. В общем-то, это еще. В 1987 году было зарегистрировано одно событие. Это вот, исходя из наших данных, мы вот такое ограничение на частоту коллапсов в нашей галактике даем.
Это получается сколько лет? 15 лет, да? Но вы подобрались близко, еще немножко, где-то надо 25 лет. И все. Но это уже будущее поколение.
Да, это уже.
Ну, раз в 20 лет, где-то 25 лет взрывается.
Так, у меня...
Окей. We have time for questions. Please.
Could you really state that no supernova event occurred in our galaxy during this period? Можете ли вы утверждать, что ни единой взрывной звезды не взорвалось в нашей галактике за отчетный период?
Естественно, на этом основывается вот это ограничение, что как бы нет. Но при условии, что вот модель, которая дает светимость, нейтриновую светимость, то есть стандартная нейтриновая светимость, если она реальная, то есть правильная, то да, в нашей галактике не было.
Не совсем так. Если вы говорите 20 килопарсек, то вы противоположный, так сказать, за галактический центр, а если двинетесь, то это 20 килопарсек и есть. У вас вы не все смотрите.
Начиная от Солнца, начиная от Солнца, это 85, что ли, процентов звезд нашей галактики сосредоточены в этих 20.
85, с этим согласен.
Пока нет открытия, происходит.
А временных окон в наблюдениях у вас не бывает?
Окна есть. Есть.
Не, ну, у нас есть пробелы. В смысле, как? Там профилактические работы, какая-то авария или что-то. Вот в этот момент имеет право коллапс произойти.
Безболезненно.
А вы можете ли быть чувствительным, чтобы видеть дальше?
Нет.
Надо объем.
Да, значительно, очень значительное
А
увеличение.
какой там материал у вас?
Нет, у нас в счетчиках керосин. Это углерод.
Керосин.
Да.
Other questions? If not, we have time for. Let us thank speaker. And we have time for. Все? Благодарность писать. В 3 часа ночи. We will start at 3 o'clock in the afternoon.
Return, please, here. Okay. At 3 o'clock next day.
Ну,